Okay, it's finally Optimus Prime time. So we're going to be testing little Optimus here. If you don't know what Optimus is, then you may need to back up like 3 or 4 videos. I don't know where we're at now. But what this is a transformer rescue fuse. Now this one's different because it has 2 PTCs in parallel. But the idea behind this is it can kind of substitute for a fuse to protect the transformer, diagnose shorts, things like that. Anyway, we'll be testing this. I've decided that I'm probably not going to show a bunch of scope setup stuff. I'm probably just going to capture the waveforms and then we'll talk about them. So let me get set up and then we'll talk about it. Let me show my setup here. Oh, who knows what this is? This is the makings of another video, but who knows what this really is. If you live in Florida, you may have never actually seen one of these. If you live in New Jersey, this little guy right here has made your life difficult more than once, in more than one way. Anyways, who knows what that is? Just put it in the comments. I'm connected up here to my isolation transformer to keep everything safe, or safer, I should say. I'm going straight into a normal HVAC transformer. This is just 24 volts AC out the secondary. I'm using a contactor, I'm manually activating it just to short the secondary. I have my amp clamp hooked up. Let's short this secondary. Oh, let me point this out as well. This transformer's protected by a 3.7 amp fuse. I believe this is a 70 VA transformer. Anyways, let's short this transformer and see what happens. I'll reset this to 0. All right. Whoa, went off screen. I might need to go into 60 amp mode. Let me do that again. I set my amp clamp up to the 60 amp mode so we can capture a lot higher amperage. One thing I want to point out is that even though the clamp is putting out volts, what you're seeing on the screen is amps. I've written a mathematical formula into the probe section that will basically take that voltage and convert it to the corresponding amperage. So what you're seeing on the screen is actually amps. Now, who watched the prerequisite? Be honest now. If you didn't watch it, I understand. I completely understand. Let me just say a few things and hopefully this makes sense. The AC current is in a sine wave, obviously, because the voltage is in a sine wave. Now, what I've done is taken cursors and bracketed this so we know how long it took. This is a zoomed in portion. You can see down here, this is the entire wave. I zoomed in just to the short. So I have cursors here so we can look at the time. I also, so the current that your digital clamp meter displays is not the peak current. It's going to be the RMS value, and that's what this line represents, the RMS value of this current. So if you were to have clamped these wires with a clamp meter, what would you have seen? This right here. So the breaker allowed the short for about 445 milliseconds. It also, the short had a current of 23.5. And don't worry about writing these numbers down. I'll try and write them down and then we'll compare them all at the end. So let me set up something else and then we'll go from there. All right, it's Optimus time. Poor little Optimus is about to be shorted. It's okay though, he's tough enough to handle it. I'm gonna short Optimus and we're gonna see what the waveform looks like. And then I'm going to clean it up and we'll talk about it. So let me reset this to 0. All right, here goes Optimus. Okay. Let's look at the waveform. So you can see that initially the PTCs allowed a lot of current, and then that current begins to taper off and then eventually goes to 0. What's happening there is that the PTCs are heating up and the resistance is increasing, but it's not instantaneous. So they sort of taper the current off and then eventually get hot enough where they pretty much go open circuit. You can see that detail here. And if we want to look at the value, I'm just going to estimate it. The RMS value of this waveform is probably like 1 amp. So really not bad. This entire short took place over 454 milliseconds, and it was 21.45 amps RMS. So that to me is pretty great. We have something that pretty much mirrors the circuit breaker that the manufacturer is using in the transformer, but it's auto reset, and it's also, with having 2 PTCs, going to allow more current, not a short, we're just talking about just regular load. It's going to allow more loads to be on the circuit than it would if it only had 1 PTC. So next, I think we're going to look and see how much of a load will little Optimus allow before he starts to get unhappy. So Optimus is the optimal protection, at least for a 70 VA transformer. Here's the setup. Oh, what a rat's nest. We're using DC voltage 26.1. Sorry, that's out of focus. I get it out of the frame. 26.1. Then I have my electronic load hooked up. So we're just going to use DC voltage because I don't have an AC electronic load. Let me go ahead and put some amps on this. I'll capture the waveform and then clean it up and we'll talk about it. Here's little Optimus's results. You'll see we have DC current now. And if, big if there, you were able to make it through the prerequisite video without dying of boredom, you'll know that DC current is very comparable to RMS AC current. So this is an okay comparison to what Optimus would do in a 26 volt AC circuit. I started him off at 2 amps, held that for a while. It looked like he was going to hold that for a long time, so I just bumped it up to 2.5. He held that for a while, and for a second I thought he was going to hold that for a long time, but then got too hot and went open circuit. I gave him a breather and then started him back off at 2, and I wanted to see if this would have fallen off eventually or if we could go longer, and it looks like we went quite a bit longer. Then I bumped it up to 2.3 and we went even longer. Then, just to make sure that this wasn't the 2.5 wasn't a fluke, I bumped it up again, and sure enough we dropped out pretty quick. He was already pretty hot at this point, so it didn't take long for a little bit of extra current to make him drop out. Now the truth is, could he hold 2 amps or 2.3 amps for, say, 2 hours, 2-3 hours? I don't know. I wasn't going to wait for that to, I just wasn't going to wait around to see. So sometimes PTCs and stuff, they can hold right at their threshold current for a long time, and you might think that it can hold it forever, but nah, there's still a time limit. But because this current is such a flat line and it seems pretty sustainable, like I was able to jump up from 2 to 2.3 without suddenly getting like a dropout. It looked to me like he could handle 2.3 for as long as 2. I'm willing to bet that 2 amps is something that he could sustain for a pretty long time. My time base here, so between divisions, is 100 seconds. Let's use some cursors to see what we have here. So he was holding 2 amps for about 4 minutes, and then he went and held the 2.3 for another 4 minutes. And then it really didn't take long at 2.5. He held that for about a minute, 50 seconds, and then dropped out. So let's look at the results. We have a transformer breaker allowing 23.5 amps for about a half a second. Then we have Optimus at allowing 21.45 amps for, again, about a half a second. So if I supply a circuit with 2 amps at 26 volts, which is what Optimus was doing, that's about a 52 VA circuit we have there. If we're able to supply 2.3 amps, we're at about 60 VA. Now, to give you some perspective, 2.3 amps can supply about 10 contactors, providing they don't all turn on at the exact same time. Now, we want to, in electronics design, whatever your max is, you drop down from that in order to create a little breathing room. So we might say that Optimus can supply a 1.5 amp circuit pretty well, and that would give us about 6.5 contactors. So if you ever needed a half a contactor over 6, he could do a half a contactor. But anyways, I would, we are over. So would this smoke a 40, would a 2.3 amp draw smoke a 40 amp transformer? Maybe over time, but you got to keep in mind that manufacturers are designing, well, who knows nowadays, but typically they design their devices to take more abuse than what they're rated for. So probably Optimus would be fine on a 40 VA transformer. The other thing is, it would be extremely rare on that circuit that you would have exactly 2.3 amps. I mean, it would have to be such a very, very rare, unique short that would provide you with exactly that amount of amperage, so that Optimus is allowing that through the circuit long enough to smoke a 40 VA transformer. Because as you can see, I mean, what kind of residential or light commercial circuit are you really gonna be supplying that would have 2.3 amps of load? You can have a lot of crap on a circuit, especially because it's not all going to be activated at one time. But even my system, if you haven't happened to catch the video where I just went through and filmed a few things, with all of that crap on there, I'm only at like 1.5 amps or something, So I think the results for Optimus are pretty promising. I feel like the normal God, why can't I think of the I always mess this name up. It just gets jumbled in my head. Transformer rescue fuse, the normal transformer rescue fuse, I think is just fine. I really think that it's pretty much good enough for our needs, but Optimus, he's a little bit tougher, can supply a little more current. He's a little closer to what a manufacturer's protection is, so there could be some advantages there. Anyways, I hope y'all enjoyed the video.